a wonderful thing. Everyone calls it, oh, hello there. So, clocks. That's what measures time, right? Well, what happens? That particular unit that we're trying to define as time is a whole frick ton smaller than our best apparatus of measurement at the time. Well, you all know what that means. We conjecture
Although
ahead.
this is going to be weird, and it's going to be about a different.
Title of the conference was something like Ground Truth or Turtles All the Way Down. And so it seems as though there's one Ruliad. I don't think it rules them all. And it might
Yeah,
be just hyper Rulial Turtles all the way down.
Yes, it's on the back of an infinite number of hyperrulial turtles.
Various people are commenting on the outrage of hacking the universe on a MacBook Air.
Hey guys, what's going on? Memes here. So, yes, we've done this before. We're gonna do it again. Why? Because we're starting to learn a heck of a lot more. And actually, rather than just chicken typing the things in and be like, I hope it comes up and making all these mistakes, I started to just go through the Planck constants. Going, all right, I've typed in enough numbers and stuff into Wolfram Alpha. Starting to gain a level of confidence. What can we figure out? All right. So as we saw before, we had our friend here. Yes, this is from Thad's. I believe this is actually source code. Actually, no, I think this is 44. But as we can see here, let's embed it. Okay. So what is this? It's also in the thumbnail for mimetic reasons. We'll go with. All right, we're talking about chapter 1. The make it big in it. All right. The minimum partition balance. Because as we know, at least for the constants of nature, at least the dimensional ingredients we need to make up our realm of persistence, to the best of our measurements and knowledge at this time, happen to be time, space, charge, mass, and temperature. It's a very interesting, sometimes it's a very complex recipe. Like the Boltzmann's constant's got all this, even Planck's constant, and gravity. They have mass in them. Why? Well, because they can. And it happens to work for us. But okay, these are just some quick things to take note of. All right, we're not going to go into this whole crazy diagram. It's I thought I understood it. I'm like, I understand. I didn't understand it. Now it's starting to make some more sense. Okay, so the action of the minimal arena is 5-dimensional. It decomposes into 5 unique geometric balances. Balances 0 through 4. We're going to see why. Okay. So you go into all these amalgamations and everything, but all you really need to know for our current thing is the decomposition. There's some cool math and logic around, but we're basing this model. I happen to colloquially refer to it as the H of Fate model because, yes, where the unit of balance 0 and balance 1 define the internal double cover domain. Okay, the hyperbolic figure 8 knot. And basically, once you go up to the domain of temperature, the really big thing out here, you get into the domain of temperature and basically an hypersphere maximal volume. That was the whole eternal cyclic cosmology video I posted before. But okay, not to belabor the point, even though I happen to be really great at doing that. Welcome, Whitechapel. Thank you for joining, my friend. But oh my God, I forgot to put all the extra things in the doobly doo. I apologize, everybody. Shout out to my patrons. Dave M, Joe Franco, and T Carr. This broadcast is helped made possible by viewers like you. Nothing wrong with a PBS model. But, all right, we go back over to our friend over here, Wolfram Alpha. All right, it's not on Wolfram Alpha, it's on a tab for the Planck time. Because, yeah, let's actually just get into this. Planck time. All right. From Wikipedia. I need to remember to put these all the doobly doo. Okay. Uh, There we go. I'm making that. All right. The Planck time is the length of time at which no smaller meaningful length can be validly measured due to the indeterminacy expressed by Werner Heisenberg's uncertainty principle. Theoretically, it's the shortest time measurement that is possible. Planck time is roughly 10 to the negative 43 seconds. However, to date, the small time interval measured was 10 to the negative 21 seconds, the zeptosecond. Okay, so yeah, we're over like 20 orders of magnitude off of being able to conceptually measure what the Planck time may be. How, may you ask, can we try to figure this out? Well, we have some equations here. We'll go down. As we can see here, the Planck time is defined by the time Planck is the square root of h, which is Planck's constant. Oh, if h bar there. Oh, that's the reduced Planck's constant. Hmm. Oh, wait. No, no, no. Okay, they have it over there. Wait, is that right or wrong? That's that's interesting. Oh well, we'll look it up after. For our convention here, all right. So Planck's constant times gravity, square root of that over 2 pi times the speed of light raised to the fifth. Fifth, they say. All I know is 5 is a pretty cool number. And weren't we talking about a minimal arena that was 5-dimensional? Now, again, this derivation, speed of light, basically typically defined as the Planck length divided by the Planck time. We have 5 of those there. How very interesting. And yeah, that reduces to, okay, yeah. Okay. So, well, that is actually Planck's constant. But since you're dividing that by 2 pi, you get reduced Planck's constant. There we go. Oh, I think this is wrong. Yeah, because that's h bar. It's got the little thingy on it. Okay, so that makes sense. So basically, square root of reduced Planck's constant times big G, gravity. We had a video on that. And that's divided by the speed of light raised to the fifth. That equals length Planck divided by the speed of light. Huh. I think that's really cool. Okay. So what do we got for our code data? So NIST Planck time, numerical value, we identify as 5.391247 times 10 to the negative 44 seconds. That's a really freaking short time. That's a really tiny turtle in medical physics, let's say. And that's got error bars of 60 for the last 2 digits, so we got up or down. Okay. This is one of the things that kind of confused me for a while. Okay. So how the heck could we go about figuring out something like this? How could we try to derive something so frickin' small? There was only a tool and a method we could use to perhaps search the computational universe for a potential, beautiful, in my opinion, closed form. Well, Thad already did that, so it's over here. We've done this before, and we'll do it again. A little bit more insight about rather than just chicken picking things in here. Okay, so what's this thing? The link's in the doobly-doo for this. All right, so we got pi. Pi is important. Why? Who doesn't like pi? We multiply that by the hyperbolic sine equation, and that's squared. Okay, and it's multiplied by 1/2 squared times e to the base of natural logarithms, and we're solving for x, that exponential over there. And we just happen to set it equal to exclamation point 5. Why? We go down. Okay. So that exclamation point would be the number of permutations or derangements, the number of ways you can arrange 5 different things. So just conceptually, hypothetically, just conjecture, we were to have, let's say, I don't know, 5-dimensional ingredients. How many ways could you arrange those 5 things? Well, it happens to be 44, which is coincidentally the name of the book is. I put it away. It's okay. It's okay. I don't want to knock myself over with MKS. That's a big book. But okay, it's 44. So what we got here? So we got pi. We got e. This is when we put our friend Wolfram Alpha, it simplifies, gives us an answer. So we got two of the major constants within mathematics, and also happen to pop up a lot in physics. We get that raised to a particular magnitude, multiplied by the hyperbolic sine function squared. Oh, times 1/4. 1/4. It's what are we with forming quadrants or something like that? It's like what are we gonna end up finding quaternions down the line? Shh, that comes later. I digress. All right. So what's it give us here? There's some alternate forms. That's actually kind of cool. Okay. So I've had this. Hold on, let's refresh this page so we can actually do it. So gives you the answers. Okay. Approximate form. Oh, look at all those logs. They're important, I hear. We can go as many digits as we want since we got a hyperbolic sign in there. It's like, oh, that sounds like it's really involved with geometry and stuff. I'm just saying. But okay, we have this. Okay, this number over here. It doesn't have the exponent. Okay, I know. We're calculating for the magnitude right now. Oh, where's the negative 44? Now again, this is one of the reasons going through and trying to reproduce, or at least have. Not me. I've assisted with it a little bit of some stuff recently. Uh, reproduce the parameters of quantum field theory and chemistry, and if we go all the way up through the periodic table, um, at that point, that would help support the conjecture here. Because, okay, 44 is a magnitude. Now, that's not negative, okay? But it is a magnitude. How does that even work? I think when Thad releases one of the new videos, we actually might start to explain that. Um, it's not just because 10 is cool and a lot of humans less enough to not lost digits and stuff. Uh, we tend to have 10, not always, but it's not just a basically the reason is, well, if you got a double cover system of 5 dimensions, 5 and 2, that's 10. So I mean, it sounds like it's far too simple a reason. It really might explain a lot. Um, I digress. Okay. Does this number even hit anything of reality? Because it's like, okay, we got pi, we got e, we've got an exponential. We're solving for here. We get the hyperbolic sine function squared, and we're quadranting it up. Okay. So the number we're looking for is 5.391. 5.391. Okay. 247. 258. Ah, you're wrong means you are incorrect. Absolutely. Oh yeah, we got error bars of 60 here. So that means that could flip up. That could actually technically be a 3. You want to go to the more of a magnitude there on the extreme. But so 4, 7, 5, 8. All right, so that's 1.1. All right, that's I don't know, what's that, like 0.2 sigma, 0.3 sigma, something like that off within the error bars. And you know what? It's also very fascinating once we start to plot this and everything. Hold on, let's see. Can we? I should know how to do this now. Plot. Da-da-da. Wait, I don't set it equal to it. So let it do its magic. Nope, that was underwhelming. Okay, that's fine. But all right, I'm gonna conjecture, make a claim. This looks like a geometric derivation of the Planck time. Gives us the units, gives us the closed form, and using this number up to about 14, 15 significant digits, along with the other Planck constants. Oh yeah, it's Planck week. We're gonna go through all. I've only done this one before because basically Thad kind of like hand walked me through this. It was the only one I was really able to put in by myself. Now it's like I skipped ahead, did a couple of. I'm like, oh, I actually kind of know. I'll have a bit of a semblance of what I'm actually doing now. I think that's pretty neat. But yeah, I think we covered all that stuff. Yeah, I think that's good for now. But hey, thank you all for watching. Peace out, everybody. Take care of yourselves. It's a wacky and wild world out there. You never know what's coming, but I think some great things are right on the horizon. Take care of yourself.